as quickly as possible. So let me jump to the this particular slide. So if you look at this slide, so consider this particular scenario where the base station is static, mobile is static. When mobile is inside the house, it is static. The tree is static. This reflector is also static. So everything is static. So you have only multipaths, which results in a particular delay. Okay, there is no time variation. Whereas if you look at this particular figure, the delay is the same, but you have time variation. So this is frequency selective, this is time selective, but in real scenario, you will have doubly selective channel where you have both delay and the time variation. So how to design the waveforms, particularly for this kind of scenario, where you have both delay and the time variation in the channel impulse response. Okay. So let me discuss how to represent this kind of doubly selective channels in different ways. Okay. The first is, we have already seen, this is the typical impulse response vector, which depends on the delay tau and the time variation t. Okay, so these are the time variables. So we can take Fourier transform with respect to both of them, and this results in 4 different representations. So if you take the Fourier transform with respect to tau, it results in HTF. This delay tau gets converted to frequency f. Okay, so this is the Fourier transform with respect to tau. So if I take the Fourier transform with respect to the time t, we get this response, which is known as the response in the delayed Doppler domain. So this figure shows this all 4 representations. We have this final this representations where we take the Fourier transform of this delayed Doppler response with respect to the variable tau. Okay, so typically we represent the wireless channels in the this delay time domain. Okay, this is the typical characterization of the wireless channels in the delay time domain. So if I move from, if I take the Fourier transform, we move from delay time to delay Doppler. Okay, here we take the Fourier transform with respect to the time. This t gets converted to the Doppler. The time variation gets converted to the Doppler. So similarly, we can move from the delay time domain to time frequency domain. Here we have to move, we have to take the FFT with respect to the variable tau. Okay, these are the 3 main domain which I'll be considering: delay time, delay Doppler, and time frequency. Okay, so what is the benefit of representing a wireless signal in the delay Doppler domain? So in delay time domain, so this diagram is from this particular book, Wireless Communication by Andrew Mullis. So in the delay time domain, the frequency response for a particular scenario is shown here. Okay, this particular axis is delay, this is an absolute time, and this is the received power in dBm. As you can see, this response is not sparse. Whereas the same response, if you view from the delay Doppler domain, it becomes sparse. So other special features are separability. The multipaths can be separated quite easily when we represent the channel in the delay Doppler domain, and the stability. This delay Doppler domain response remains static for longer duration compared to the delay time domain. Okay. So this representation of wireless channel in the delay Doppler domain has been already done in 1974 by Bellow. It is available in Bellow's that classic paper on characterization of the standard doubly selective channels. So what is new in orthogonal time frequency space modulation? The new thing is that we insert the information symbols in the delay Doppler domain. Unlike in WebDM, where we put the information in the frequency domain, we put the information symbols in the delay Doppler domain in the case of orthogonal time frequency space modulation. So let me just quickly explain what is WebDM. So we put the information in the frequency domain. We move to the time domain by performing IFFT. We put the cyclic prefix, and this is the operation. So if you look at this particular diagram, so you have subcarriers here. So this is one particular WebDM symbol. That is another particular WebDM symbols. So we can say that the WebDM operates in the time frequency domain. Okay. So what is the problem of WebDM in high Doppler scenario? Okay. So these are the subcarriers. Okay. These are the subcarriers. At the sampling time, only the intended subcarriers should be present. But because of the Doppler shift, the subcarriers, here you do not get any intercarrier interference, because at this particular sampling time, only this pulse is active. However, if you take sample at this particular time, apart from the intended subcarrier, you have other subcarriers present. So that is known as intercarrier interference, and that happens due to high Doppler in modern communication systems. So let me explain from this diagram. Okay, so ultimately the signal to be transmitted has to be in the time domain. Okay. So here, this is the signal to be transmitted. Okay. And OFDM, we are in this particular frequency domain. Okay. And in OTFS, we are in the delay Doppler domain. So what we do, in the original paper by Ronnie Hadani, so we move from the delay Doppler domain to the OFDM by performing what is called as inverse symplectic Fourier transform. We move from delay Doppler domain to the this is frequency domain, time frequency domain, and then we perform IFFT to arrive at X. So in that way, OTFS, the classical OTFS, that which people are calling as OTFS 1.0, is nothing but some kind of pre-coded OFDM. But recently, Professor Saif from IIT Delhi and his collaborators have shown that we can actually jump directly from delay Doppler domain to the time domain. So this version of OTFS is known as OTFS 2.0. There are certain advantages of performing this direct jump from delay Doppler domain to the time domain. Okay, that can be called as Jack transform based OTFS. Okay, so what's the good thing? The good thing is that there exists a set of time domain signals localized simultaneously in delay and Doppler, which can be used as basis signals. So ultimately, if you compare different waveforms, you have to basically compare the basis functions. If you are able to identify the basis functions and we can compare the basis functions, then we can actually compare them effectively and correctly. Okay. This also, the question is why OTFS performs better than OFDM. So that is clearly mentioned in this particular paper. So this x-axis shows this particular ratio, Doppler divided by the subcarrier index. When the Doppler divided by subcarrier index is an integer multiple, in that case, OFDM and OTFS are equivalent. In other places, the fraction of interfered symbols. Okay, this is nothing but the fraction of interfered symbols. This fraction of interfered symbols is very high in all other cases. In the case of OFDM, but the delay Doppler domain, the interference is less. So what we have done in this regard is the multi-user communication using OTFS, and for multiple access we have used one particular code domain, a NOMA technique, which is sparse code multiple access. So in sparse code multiple access, we have a code book. Okay, suppose there are 6 users, we have 6 code books, and every code book contains 4 code words. That means it is the alphabet size is 4. If the first signal is, the first user decides to send the signal 1, we take out this column and we send this particular code word. If user 2 decides to send 2, we select this column. Okay. Similarly, we take out the columns from every code book and we add them up. So what is known as superposition coding, and that is transmitted over the channel. And the job of the multi-user detector is to detect the individual code word from the sum vector. So here the specialty is that every code word is a vector code word. Unlike QPSK is a complex scalar, but here in this case these are complex, but this is a vector code word. At the same time, these are sparse. Okay, you can see that the number of non-zero is only 2. So this gives a lot of shaping in to the code book system, and also because of the sparsity, we can actually have low complexity detector. Okay, so in this first word, so we have designed how to allocate the sparse code multiple access code words over the delay Doppler grid. So in OTFS, we maintain this kind of grid. In OFDM, we maintain time frequency grid. So in OTFS, we maintain delay Doppler grid. Okay. So there are 2 schemes. Okay. So these are all SCMA code words. So we can align these code words along the Doppler bins, which is called as scheme 1. In scheme 2, we can align the code words horizontally along the delay bins. Okay. So we have compared these 2 schemes, and we can actually arrive at a better scheme if we know the channel at the transmitter side. So this particular figure shows the block diagram for OTFS SCMA in the case of downlink. Okay. So in the case of downlink, we do the superposition first, and then the superimposed code word is transmitted. So here we allocate. Okay, there are J users. We allocate the SCMA code words over the delay Doppler grid. Okay, and we take out this SCMA code words. Okay, these are the delay Doppler grids. Okay. These delay Doppler grids are added to get the overall superimposed delay Doppler grid. Okay, so then we perform the OTFS modulation, and the receiver structure is straightforward. In the case of downlink, we perform OTFS demodulation. After OTFS demodulation, we perform OTFS equalization based on MMSC equalizer, and then we perform the sparse code multiple access detector. This is the block diagram for OTFS SCMA in the downlink. Coming to OTFS SCMA in the uplink, the scenario is a little bit different. Okay, so here these are the users. Okay, so these users sent data towards the base station. So now here the superposition will happen later. First the channel interaction will happen, and then the superposition will happen. So because of that, OTFS and the SCMA are not cannot be distinguished. Okay, so for that we have actually, this is the crucial contribution to this work. We have designed a single stage message passing algorithm. So if you notice from this, this is the typical sum product rule. Okay, so in the sum product rule, so here what is happening is, it's very difficult to combine two detectors in a particular single tenor graph. Okay, so but here the good thing is that we can actually multiply the channel coefficients as a 1 by p vector, and this code word as p by 1 vector, so that their multiplication is a scalar. So this multiplication will be scalar. So we use this trick to simplify the sum product rule that can be used in the message passing detection in OTFS SCMA in uplink. Okay. The complexity is a little bit more, but however, the performance, we didn't use any approximation. We derived the diversity analysis of OTFS SCMA. So we could find out that in the downlink case, the diversity order is given by the number of distinct Doppler taps. How many distinct Doppler taps are there in the channel? So the scheme 1, that gives the diversity order. In scheme 2, the number of distinct delay taps. How many distinct delay taps are there? Depending on that, we can actually derive the diversity order. So this table shows the summary of this diversity analysis. So we can actually propose another pattern if you know the channel, delay Doppler channel in the transmitter side. Okay. So here we can actually, so this is one particular code word, these are one particular code word. We can swap the first element of the another particular code word with the another element of another code word. Okay. So here, for example, this C1, and this C2, they will be exchanged. So that can be done provided we know the delay Doppler channel at the transmitter side. We can actually nullify the way the two-dimensional convolution happens at the transmitter side in the case of OTFS. So this is known as the scheme 3. So this shows the algorithm. So we propose one channel estimation technique using convolutional sparse coding, and this paper was published in 2022 along with my PhD student. So here we used a pilot vector. Instead of a pilot element, we used a pilot vector. So you have 6 users. So we use 6 pilot vectors like that. So convolutional sparse coding is that. So this kind of diagonal structure is coming due to the convolution operation. Okay. So this convolutional sparse coding technique is a well-known technique in the literature of compressive sensing. So using that technique, we could actually find a similarity of OTFS SCMA. As I have said, this diagonal strip is coming due to the convolution operation, and these vectors are coming due to the sparse code multiple access code words. So we could find out immediate connection between OTFS SCMA channel estimation and convolutional sparse coding. So using that technique of convolutional sparse coding, we proposed a channel estimation technique. Yeah, this is the same figure. So for 6 users, these are the OTFS delay Doppler grid. So we put this. These are the pilots. These are the pilots. Okay, we have to put sufficient guard band. So as to ensure that there is no interaction. Okay. We also propose. We found out what should be the minimum length of the pilot vector. Okay, for this particular channel. Okay, these are some numerical value. Okay, for EVA channel model. When these are the parameters, so this length of the pilot vector must be 20. Okay, this is done using some analysis. We have also found out the Kramer-Rao lower bound, but I decided not to keep in the slide. Okay, so currently we are working in these 2 particular fonts. Design of OTFS for other multiple access techniques like rate splitting multiple access, pattern division multiple access, and we are also working. So in OTFS, different variants have come up like JAG OTFS. Orthogonal delay Doppler division multiplexing. So there are different versions. Okay, how to compare these different versions? So we are working to find out the basis functions of these different versions, and we are trying to compare the diversity orders of these versions. And with every version, there are like two versions. Like in Jack, we have continuous Jack OTFS, we have discrete Jack OTFS. So this continuous Jack OTFS, discrete Jack OTFS, they are different. Their basis functions are also different. So we are working on to find out what are the exact differences. In certain cases, if the pulse is a rectangular pulse, all these variants are the same. So the difference comes when the pulse is different. Pulse is not rectangular. Okay. So for this kind of scenario, we are actually trying to study this variance of OTFS under the same umbrella. So these are the current works that I'm involved in. So sorry, I had to quickly wind it up. So any questions?
Long live India and France friendship.